In the classroom to go to college. Now there's a new one.
By collecting the light from a distant star and splitting it into its component colors, astronomers can learn a staggering amount of information about an object that may be millions of light years away.
All the color in the light of a distant star is mixed into a composite image at the retina of the eye, and we can spread it out into an orderly array and study it. This is spectroscopy, and without it, the universe would be incomprehensible.
Light is the natural phenomenon that stimulates the remarkable mechanism of the human eye and allows us to perceive the infinite visual variety which the world and the universe have to offer. And perhaps the most pleasurable visual experience is the eye's ability to distinguish between the various colors of the spectrum, the endless variety of colors on the Earth, and from throughout the universe. We usually think of the visible light from the sun or from an artificial light source as being white. But what we perceive as white light is actually a mixture of distinct colors. And for centuries, we've known that white light can be separated into the different hues of the color spectrum, from red to violet, by passing it through a glass prism. In a classic experiment, Isaac Newton produced the color spectrum by passing daylight through a prism, then recombined the various colors by reflecting each color onto a single point. And once again, the resulting spot of light was obviously white. This proved that the various colors were simply component parts of what we perceive as white light. Since visible light is a form of energy, it's logical to assume that the various component colors represent different levels of energy. For instance, red has the lowest energy level of all the colors in the visible spectrum. Orange has a slightly higher level of energy. Yellow is more energetic than orange. And green is more energetic than yellow. Blue is more energetic still. And violet is the most energetic form of visible light. So the various components of white light, the colors of the spectrum, are really just radiations at varying levels of energy. Also, the component colors of visible light serve as the cornerstone of spectroscopy. Spectroscopy is the technique by which astronomers can determine a remarkable amount of information about a distant star by recording and analyzing its visible light.
We use the science of spectroscopy to identify elements, both here on the Earth and out in space. And it's that identification then that tells us what objects like stars and galaxies are made of. Well, it's fortunate for us that much of the material out in space is in the form of hot, glowing gas, because it's the light from that hot, glowing gas that we analyze, and from that analysis, we determine what the gases are made of. Here on Earth, most gases are invisible, and so we can't identify them just from their appearance. This room, for example, is full of gas. It's full of nitrogen and oxygen, but we can't tell that just by looking at it. This tube is full of hydrogen, and we can't tell that just by looking at it. You have to take my word for it. But notice what happens if I pass an electric current through the hydrogen and cause it to glow. We see that the hydrogen glows with a bluish red light. Maybe a little bit hard to see in here because of our conditions. Here's a tube of helium, which is also invisible, but again, if we pass an electric current through the helium, we see that it glows with a pale yellow light. A tube of neon gas, when we pass a current through it, glows with a rather bright orange light. And finally, a tube of sodium gas glows with a rather distinctive bright yellow light. Hydrogen glows with a bluish red light, helium a pale yellow light, neon a bright orange light, and sodium a bright yellow light. Does that mean that whenever we see a bluish red light, that we can assume that that's glowing hydrogen? Well, that's tempting, but unfortunately it's not that simple for a variety of reasons. For one thing, there's thousands of substances and there just aren't enough colors to go around. But notice what happens if we take the light from the glowing hydrogen and we pass it through a prism. Prism that separates the light, divides it into its individual colors. A wonderful thing is observed. We see a pattern, a distinctive pattern of three colors: a shade of violet, a shade of blue, and a shade of red. That's the spectrum of hydrogen, and it turns out that no other element in the universe has that same distinctive pattern. The spectrum of helium, a little bit more complicated, but it's unique to helium. The spectrum of sodium is different from hydrogen and helium, but it's unique to sodium, and we see that there are two bright yellow lines. And the neon spectrum is unique to neon. And so every element, every substance that we find here on Earth has its own unique spectrum. Well, then the crucial question is, do the elements out in space give off the same spectral patterns as the elements here on the Earth in the laboratory? Does hydrogen out in space give off those same three characteristic lines? And the answer is yes, it does. Hydrogen out in space gives off the same shade of violet, the same shade of blue, and the same shade of red as hydrogen here in the laboratory, provided it's under the same conditions, of course. Helium out in space gives off the same spectrum as helium here on the Earth. In fact, the element helium was first discovered in the spectrum of the sun back in the 1860s, and it wasn't found here on the Earth for some 30 years later. Well, the fact that the spectral patterns out in space are the same as the spectral patterns here on the Earth leads us to some very important conclusions. In the first place, it tells us that the elements out in space, the elements that go to make up the stars and the galaxies, are the same as the elements here on the Earth. They were all made of the same stuff. Second, it tells us that we can use spectroscopy to identify those elements out in space because we know the patterns are the same. And third, it tells us that the laws of nature, the basic laws that govern the interaction between matter and energy, are the same throughout the entire visible universe. It tells us that hydrogen out in a distant galaxy behaves the same way as hydrogen here on the Earth. And that has profound implications as we try to identify and analyze the myriad of intriguing objects that we find out in the universe.
In reality, spectroscopy is much more complicated because stars are not made of single elements. Typically, the spectra of stars are composites of dozens of elements.
Well, there's no question that light is an efficient communication device. Its energy permits it to carry information, and in fact, its energy is the information. We know that light can transport data about color and brightness, and we realize that the nature of the light given off by some source is related directly to the temperature of that source. Well, for instance, a blue-white star is much hotter than, well, say, a red star. Well, although at first it appears as though the stars behave according to the rules of a so-called black body, we know from careful examination and analysis of the light of the stars that the stars are really far more complicated. Their spectra are not simply smooth, continuous rainbows of color, but instead are crossed with numerous dark lines. Well, in 1802, Wollaston first discovered these lines in the spectrum of the sun. He really didn't know what to make of them, but he thought that they might simply be the natural boundaries between the colors. Well, not long after, by 1814, 1815, Joseph Fraunhofer had very carefully looked at these lines in the sun spectrum. In fact, he had located and measured about 600 of them, gave them designations so that they could be found again and referred to. Well, these lines were so well studied by Fraunhofer that they're still called the Fraunhofer lines. But Fraunhofer, although he studied them carefully, wasn't able then to know really what made them appear.
And began to realize that these were regions of the spectra, wavelengths of light, where certain wavelengths were inhibited in passing out away from the sun. Something about the sun absorbed or prevented certain wavelengths from getting out. We know now that that something is the atoms of gas in the outer atmosphere of the sun. Each kind of atom absorbs certain wavelengths of light or of radiation. And doing so, it raises itself to higher energies, but it can only absorb certain wavelengths and move itself into certain energies according to the quantum theory. So we can tell something about the nature of the sun by the lines we see in its spectrum. First, we know what kinds of atoms there must be there. But we also know the physical state of those atoms, what their temperatures are, that is the temperature of the gas, how fast their particles are bumping into each other. We can tell something about the pressure of the gases. We can determine the relative abundances of the different chemical elements. And many more things can be learned from studying the details in the spectrum of a light source. It's one of the most powerful tools in astronomy and was thoroughly developed early in this century and has been in very constant use ever since.
Today, spectroscopy is an indispensable investigative tool for the astronomer. This is a photograph of a star field. This is a spectrogram of the same star field. At the Cerro Tololo Observatory in Chile, an astronomer checks the 60-inch telescope which he'll use to make a spectrogram of a single star. A light-proof room, one floor below the telescope, houses the spectrograph, which is too large to be attached to the telescope itself. The astronomer lines up the star whose spectrum will be photographed. Starlight entering the telescope above is reflected by a series of mirrors to a grating, which breaks the white light into its component colors. The telescope concentrates the starlight at the focal point, where a narrow slit is placed. Through the eyepiece, the astronomer can see a magnified view of the star on the slit. The shutter exposes the film, and the photograph is completed. Later, the astronomer examines the developed plate. The small absorption lines carry more information about the star than could be obtained by almost any other method. By analyzing the patterns of lines, the star's composition, temperature, and atmospheric pressure can all be determined. And because of a phenomenon called the Doppler effect, a spectrogram can also reveal the speed of the star and whether it's traveling toward the Earth or away from it.
Imagine that you stand over a pond and drop pebbles in the pond at very regular intervals, say 1 a second. As each pebble hits, a circular ripple moves out away from the center of impact. And as the pebbles keep falling, you have a whole series of concentric ripples, concentric rings, expanding away from the point where they were dropped. But now suppose you would get into a rowboat and row toward those oncoming ripples. You would see them coming at you faster because you're moving toward them. And you would feel that they were therefore closer together. Equivalently, if you rowed away from the source of the pebbles, the waves would seem to be spread out, and they would approach you farther apart or at a longer wavelength. An interesting experiment that's actually been performed is to put a bunch of musicians on a train. Now, as the train approaches, you can hear the music from the musicians, but at a slightly higher than expected frequency because of the Doppler effect. But as the train moves away, then the pitch lowers, and all the sound comes at a longer wavelength. But we still recognize the tune. It's just a slight drop in key as it goes by. But all of the different wavelengths are shifted in the same proportion. It's the same way with the spectral lines in a star. If the star is moving away from us, the whole pattern as a unit shifts to longer wavelengths. But you can recognize that pattern just as you recognize the tune from the musicians. So that you can see that this is indeed a shift of the familiar pattern of spectral lines. We can learn far more than just how fast a star might be moving toward us or away from us by measuring the shift of the spectral lines due to the Doppler effect. For example, consider the planet Saturn. It has rings revolving about it. These rings are made up of myriads of individual particles, but the sunlight reflected off them gives us the illusion of solid rings. But if we look at the spectrum of the light coming from different parts of the rings, we're looking at light reflected from particles moving away from us or toward us at different speeds. So we have a different Doppler shift in different portions of the rings, and in fact we've learned that the inner particles are moving more rapidly than the outer ones, just as planets closer to the sun go around faster than ones further out. And that's one of the proofs that the rings indeed are made up of individual particles.
For centuries, astronomers observed the heavens by studying the visible light that the human eye detects, and more recently, by making a photographic record of that visible light. But in the last few decades, a major revolution has taken place. Radio waves from space were first detected in the 1930s, and astronomers now record and study all forms of electromagnetic radiation from space, not just visible light.
The radio astronomer, his radio wave might be that long. It might be several centimeters or inches, and his telescope can only be a few hundred feet at most because it's an engineering problem to do more than that. So radio astronomers had a hard time getting resolution. They finally hit on a clever solution. They thought, we don't need a whole bowl of a radio telescope. Let's just imagine that I have that big bowl and I chop it to pieces. And as a matter of fact, most of the surfaces of radio telescopes are made of panels of different pieces. Well, just throw them all away except a couple of them, and take your telescope and take the radio waves coming in and collect them and keep track of that signal, and move these two to another pair of positions, keep track of that signal, and keep moving them till you filled in that whole bowl-shaped parabola. So that's what we've done, and it's called interferometry. And instead we have two telescopes, but we think of that as a single system, and each telescope is one piece of a much bigger telescope that you get by moving these two around through all the configurations you can imagine. And finally they discovered that we could separate them by the whole United States, or you could connect a telescope in California with one in Australia or Germany or whatever, and now you get unprecedented resolution. And if you wonder about the kind of detail we see now, if someone took a dime and held it up in New York City, and another guy looked at it from San Francisco and measured the size or the angle that that little dime made spread over these 3,000 or 4,000 miles, that would be about 1,000th of a second of arc, and that's the kind of resolution that radio astronomy is achieving today.
For the astronomer, being able to observe the entire electromagnetic spectrum instead of just visible light is like a pianist who is able to utilize all 88 notes of the keyboard instead of just one 8-note octave. They record radio waves from distant quasars, infrared radiation from cool protostars, and X-rays from exploding and dying stars. For For example, Kitt Peak astronomer Donald Hall uses infrared spectroscopy to examine stellar radiation.
Yeah, infrared astronomy tells us about cool objects or objects which are embedded in large clouds of dust and gas which are opaque at optical wavelengths. It therefore tells us in particular about very young stars being born in these clouds, and also about very old stars which are burying themselves in clouds of material they're expelling. By going to high-resolution infrared spectroscopy, one is able to obtain very detailed information about these sources. One is able to find out about the chemical composition, temperatures, pressures, even magnetic fields, whether the sources are moving towards us or away from us, and whether the material around them is contracting or expanding. The FTS is a type of spectrometer which allows us to break light, or in this case infrared radiation, up into its constituent colors. The FTS is different to conventional spectrometers in that rather than breaking the light up into individual colors and looking at them one at a time or with a number of detectors or a photographic plate, it puts all of the light onto one detector all of the time and then codes it by moving two mirrors in a very precise manner. Because the instrument is able to look at all of the light all of the time, it has big gains over previous infrared spectrometers, and so is letting us move on into a new area of infrared astronomy where we're able to study new infrared sources in great detail.
Our new technology for astronomical observations falls into two general categories. One is the kinds of observations we make from the Earth or the vicinity of the Earth. The other are the observations and studies we make of the planets, and that involves, of course, sending spacecraft actually to the planets. In terms of terrestrial observations, I think our new technologies are going to come in the area of more efficient electronic detectors, because whereas astronomers used to use film and take hours and hours to observe something, to collect the faint light that comes from the distant parts of the universe, now we have electronic detectors, and those same studies can be done in a matter of minutes. And these detectors are getting more and more efficient. And it's interesting because the motivation for this comes primarily not from astronomers, but from the general public, because these people can see cameras eventually being made with detectors and not with ordinary film. In terms of ground-based observations with telescopes, the University of Texas is proposing to build a 300-inch telescope, which will be half again as large as the telescope at Palomar Mountain, and this would be located at the McDonald Observatory in West Texas. Parallel with this, the University of California is proposing to build a 400-inch telescope, which they would probably put on Mauna Kea, on the big island of Hawaii. This would be a little different technology. This would be made up of 37 hexagonal mirrors, all in one mounting, which would be swiveled around together. So it'll be interesting to see which of those two technologies turns out to be the best. Astronomers are also studying what's called the National New Technology Telescope. This would be a 600-inch telescope, which would be 3 times as big as the Palomar telescope with about 9 times the collecting area. And this would probably go into operation in the 1990s sometime. There's been some talk of a permanent space station up in space, and although the primary reason for that station would not be astronomy, we would hope that they would have some telescopes up there and perhaps some astronomers to go up and use them. There's a gamma ray telescope that is under construction right now. That'll be a satellite, an orbiting telescope, because gamma rays, the highest, the most energetic kind of radiation we know of, don't come through the Earth's atmosphere, so they can only be observed from above the atmosphere. And it's a huge telescope, about the size of a room. It'll have 4 different detectors on it, and that will give us our first really systematic long-term studies of this high-energy part of the spectrum. We know that there's gamma ray sources out in the universe, Not sure what they are. And of course, if we really want to speculate, we'd love to put a radio telescope up in orbit and get away from a lot of the man-made radio sources that seem to be pervading the surface of the Earth. Or ideally, if we had all kinds of money, we'd put a radio telescope on the backside of the moon, because then we would get no interference from terrestrial sources. In terms of the future in planetary observations, of course, the best way to observe planets is to go there, either land or orbit or fly by. And there are a number of missions that really excite the astronomers. Of course, the Voyager spacecraft that went by Jupiter and Saturn in the late 1970s, early 80s is on its way to Uranus, and then hopefully it'll go on to Neptune. And that'll give us our first close-up look of those two distant planets toward the end of the 1980s. The Galileo mission is a very ambitious mission in which a spacecraft will go out and actually orbit the planet Jupiter and give us long-term observations of that planet and of Jupiter's satellites. And there will be a probe that will go down into Jupiter's atmosphere. So it'll give us some information about what's going on in the largest planet in our solar system. We'd like to put another spacecraft around Venus with a higher resolution radar system. The Pioneer spacecraft that orbited Venus for a number of years gave us a resolution of 2 or 3 kilometers. And we'd like to go up now with a new technology, with a radar system that would see things on the order of the size of a football field. And that would give us a pretty good idea of what kinds of geological processes are going on the surface of our nearest neighbor. To get more speculative, we'd love to go back to Mars. And we'd like to bring some samples back to the Earth, some of the Martian soil that gave us those puzzling results with the Viking spacecraft, and we'd like to be able to analyze that in our terrestrial laboratories. We'd like to put an orbiter around Saturn and get some long-term observations of that incredible ring structure around that planet. And of course, the closest object is the Moon. We've been there. And there are a number of minor planets or asteroids that come rather close to the Earth, within a few million miles of the Earth. And I'd like to see a mission go out and take a close-up look at those minor planets.